Welcome back to Bio 6612. In this lecture, I'm going to talk about implementing conditional logistic regression in R. So, generally speaking, the way that you do inference in conditional logistic regression is the same as you would in regular logistic regression. For testing individual parameters, both the likelihood ratio test and the wald test are still valid, meaning that you can use either of these to get confidence intervals or hypothesis tests for your parameter values. The likelihood ratio test is better for small sample sizes. However, wald is the default in R because it's easier to calculate. Another thing that we've already learned about for logistic regression is a goodness of fit test, where you compare a model of interest to a saturated model. And you can still use the Hosmer-Lemeshow statistic for that, which we discussed in lecture 4.4 and 5.2. So I'm going to go through a quick example about infertility after miscarriage or abortion. And in this example, a case control study was conducted in Greece in 1976 to estimate the effects of spontaneous abortion, also known as miscarriage, and induced abortions on subsequent risk of infertility. 100 cases were collected. These were women with secondary infertility, where secondary infertility is defined as the inability to become pregnant after previously giving birth. And there were two controls matched to each case. And these controls were selected to be from the same hospital as the cases. Should be case. And they're matched on a couple of variables, including age, parity, which is the number of pregnancies carried to a viable gestational age previously, and level of education. So the variables in the data set are case, that's the outcome, which is 1 for women with infertility and 0 for the healthy controls. Spontaneous, which is a variable indicating the number of miscarriages. It's categorical, 0 for 0, 1 for 1, and 2 for 2 or more. Induced, which is a variable indicating the number of induced abortions, also categorical with the same levels. A stratum, which indicates which matched set a particular observation belongs to. And then this data is actually included as part of base R. And so you can just load the data by using data and then in quotation marks the name of this data set. I'm going to factor both of the variables of interest, which are the ones related to abortions. And you can see that data set listed here you have, along with the variables of interest, which are spontaneous and induced, and that's the cases, the outcome, and stratum indicates what matching pair or matching set each person belongs to. We also get values for the 3 variables that were matched on. So there are a couple ways we could consider modeling this data. We could just ignore the matching factors altogether and run a regular logistic regression with our outcome of interest, which is case, and the covariates of interest for the induced and spontaneous abortion. That's one thing we could do. Another thing that we could consider doing is adjusting for matching factors as covariates rather than using a different type of model. And that's what I have modeled here. In this model, I'm calling model_adjusted logistic regression. And the 3 matching factors here are just controlled for as covariates in the model. And this seems like it might be a reasonable thing to do. However, one of the issues, as I discussed in the previous lecture, is that this can lead to bias in the estimates of interest. And so what happens when we just apply regular logistic regression with matched data? well we have two models here, one that's unadjusted and one that's adjusted for the matching variables of interest. And as you can see, I've actually sorted so you have the groupings here based on the variables you're interested in and one for each model. The estimates are very different. For example, comparing induced abortion in the second to the first category, you have 0.82 as your estimate for the unadjusted logistic regression and 2.59 from adjusted. Those are quite different. And that's true for all of the estimates here. So that's not good. We would hope that we have similar estimates if these models are valid. And not only are the estimates themselves different, but the inference is quite different as well. For example, with adjustment, both the spontaneous and induced abortion variables are significant, but without adjustment, only spontaneous abortion is significant. So the best thing that we would want to do here is actually to properly account for matching using conditional logistic regression. So in R, we actually use a different package to do conditional logistic regression, and we use the C-logit function from the survival package. And survival package is generally for survival analysis data. The reason that we can use the C-logit function from that package is that for one type of survival analysis, the model is actually equivalent to our conditional logistic regression model. And so our data is already in the format we need for this analysis, which is one row per patient and a variable that indicates the stratum or match set. So all we have to do to run this analysis then is to load the library and then call this C-logit function. The outcome is case. Then you call your variables of interest, these exposure variables, and then you have this added argument, strata, and then the name of the variable that tells you what the strata are, which is called stratum in this case. And then you have to tell it what data you're using. So that's what the model structure model call looks like for this function. And then I also, I collected the coefficients from this model into that same table that I showed you before so we can compare across the three different models. And the first thing I want to draw your attention to here is that we have an intercept term for both the unadjusted logistic regression and the adjusted logistic regression, but we don't have one for the conditional logistic regression. And that's because, as you saw in the way that these were, the conditional logistic regression was derived in the previous lecture, we will not have an intercept term for this type of model. However, we can compare across the other three types. And all I really want to highlight here is that now we have numbers that are a little bit closer to the adjusted model than they were to the unadjusted. And the numbers that you get from this conditional logistic regression are going to be the most valid for this type of data.